Okay, so hi everybody. So yeah, I have internet again, which is good. And okay, so it's so I suppose it's lecture 27. And there's one little loose end from the last lecture, which kind of fell through the cracks because of the internet issue. And this is that I never really explicitly discussed the initial value problem for a system of linear equations. So let's say I have a system like this. No, sorry, A, X, B. And this is exactly what you would expect. It's very easy. So there are two steps. One is you find a fundamental solution set, x1 of p through xn of p. We discussed how to do this previously. You diagonalize the matrix and so on. And then the second step is, okay, so the first step, implies that the general solution is the span of these things, right? C1, X1, P, all the way to Cn, Xn of P, where these C1 through Cn are some unknown real coefficients, or there's a subspace, right? And so the initial value problem means you're given some initial data, right? That the value of x at 0 should be some capital X naught. Right? And so now all you have to do is just define C1 and through Cn, which match this initial data. And this is just the usual thing. Just solve the linear system. So make a matrix with these things as columns. And now these unknown coefficients are what you're interested in. And the right-hand side is the actual initial values. So there's some vector capital X naught here. Okay, that looks a little bit too big, but okay. So this is the initial data. And this is always invertible by the Wronskian lemma. And we actually proved this when you get a fundamental solution set consisting of exponential functions multiplied by eigenvectors. And so that's it, that always works. And this has some jargon associated with it. This is often called, so you can view this as a matrix valued function. Let's call it capital X at 0. And this is called the fundamental matrix. This is just jargon because we're not doing anything really new with it. I just want to be consistent with the book. It's called the fundamental matrix. So this is like really straightforward, and I won't discuss it more. And if you did the homework, you understand how it works. So any questions about this? Okay. So now let's move on to today's lecture, which is really cool. But what does it say next to the X matrix? The fundamental matrix. That's what this is called. So this is a function of T. It's a matrix valued function of T. The top one. Initial data. This is not a matrix. This is a vector. Okay. This. Okay. This says always invertible. Okay, I will write more slowly now. Okay, so let's now move on to the topic of today's lecture, which is just a second. I just want to make sure this is Is the lecture being recorded? For some reason, I can't see.
Yeah.
Okay, good. Okay, so now let's move on to today's lecture, which are going to be two topics: is inner product spaces, and the other is Fourier series, which are some of the most useful things in the course. There are many useful things in the course. So let's start with inner product spaces. So setup is, well, recall what we did in chapter 6. We defined this concept called the dot product. So if you have two vectors in Rn, then we define their dot product to be just X transpose Y, which was, just the sum. So we all know what it is. And from this concept, we got lots of other derived interesting concepts, right? So we got the concept of a norm, measures the length. We got a concept of orthogonality, dot product being 0. And we got the concept of an orthogonal basis. And then once we had that, we got, a projection onto a subspace, formula in terms of orthogonal basis. We got the best approximation theorem and the decomposition theorem. And we even found a way to turn any basis into an orthogonal basis, namely Gram-Schmidt. Okay, so this one concept led to all of this useful stuff. So what we're going to do now, which is section 6.7, which I saved until now because the main example is going to come now, is a generalization of the dot product to any vector space. It's a way of generalizing all of these concepts to vector spaces that are not Rn, right? So the key was here, this was Rn. Now, so this is a generalization to any vector space, and that's what's called an inner product. Let's write a definition. So an inner product space is a vector space V, so just any vector space. Now it has, so a vector space has vectors, it has addition and scalar multiplication. An inner product space has one more thing. It has an inner product, which is a generalization with dot product. So along with an inner product. What's an inner product? An inner product is a function which takes two vectors that live in the vector space and maps them to a real number denoted U inner product. Okay, so it's a function, the input is two vectors and the output is a real number, just like the dot product. Satisfying four properties. And these are the four, again, this is like, the dirty secret, the way we generalized everything before the first midterm to arbitrary vector spaces. We actually only use four properties of the dot product in everything. What are the four properties? The four properties are the dot product is commutative, so the order doesn't matter. Second property is it's linear, so if you take two vectors and take their dot product with the third vector, it's equal to the sum of the dot products, sum of the inner product, sorry. Yeah, so these properties are all satisfied by the dot. The third property is, if you multiply one of the vectors by a scalar, just multiplies the inner product by a scalar. And the fourth property is that if you take a vector and inner product it with itself, you get something non-negative. So that's called an inner product space. It's an abstraction of dot product. And the key is that these are the only four properties we need. So this is again the, if it tastes like butter, it's butter philosophy. And this is what it means to taste like butter. Okay, and once you have this dot, once you have an inner product, the punchline is you get all of this stuff up here. All of this stuff works exactly the same way. Okay, so the punchline, all of chapter 6 still works. Okay, and the reason it still works is actually if you look in all the proofs, the only thing we used is the Pythagorean theorem. Okay, and you can check that these 4 properties imply the Pythagorean theorem. These imply that the norm of u plus v squared is equal to norm of u squared plus norm of v squared when u inner product v is equal to 0. That's an exercise you can do. Okay, somebody is asking, do the brackets mean multiplication? How does this belong in R? Okay, I haven't given you an example of this. So the function is this brackets. This may be a new concept. Okay, maybe I'll give you some examples and it'll make more sense. So given a vector space, you can define a function denoted by these brackets, okay, which then takes, it's not the dot product, it's the inner product. Okay, so I haven't defined what, okay, let me show you some examples. Okay, it's not the dot product, it's anything with these properties. So let me show you some examples of inner product spaces and inner product. Maybe that'll clarify that. Somebody asked, this for real vector space? Yes, this is all for real vector spaces. Scalars are real. Okay, so let me show you some examples. The first example is you take the vector space to be Rn, and you literally define the inner product of 2 vectors to be this, which is just the dot product. Okay, so the dot product is one example of a function of vectors, a real valued function of 2 vectors that satisfies all 4 of these conditions. Okay, we already can see that. But the interesting thing is there are lots of other vector spaces and functions that satisfy these properties. So here's another example. Let's take V to be the vector space of continuous functions on the interval -1 to 1. Real valued, continuous. So that's a vector space. You can add those things and scale and multiply them by real. Now I'm going to define an inner product on this. Okay, maybe this is what people were confused about. You have to, just like we defined the dot product, you have to define an inner product. So what's the inner product? I'm going to define the inner product of 2 functions to be the integral of the product. Okay. So that's now a vector space and this function called an inner product. And now I'm going to check that it satisfies 1 through 4. So let's just go back. So you have to check these 4 properties. Okay. So I wrote down some function. Does it have all 4 of these properties? Well, it actually does, right? So let's just check some of them. So the integral, I'll just check a couple of them. So one is f inner product g is integral of f of x g of x dx, which is integral of g of x f of x dx, which is g inner product f. Okay. Yes, we're not using complex numbers. Forget about complex numbers. Okay. So one checks out. And similarly, you can check all the other ones. They just follow from properties of integrals. Okay. So this means this is an inner product space. Okay, so somebody asked, one of the requirements is the inner product of a vector with itself has to be non-negative. Okay, let's check that. What's f dot f? That's integral of f of x squared dx, and that's non-negative, right? So we check property 4 also, right? So maybe this is what people are missing, that an inner product space is not just a vector space. It's a vector space with a specification of inner product. And there can be more than one inner product on a given vector space. Okay? So the package that counts as the inner product space is both these things. Okay? Okay. So that's another example. And now, let me just to clarify what it means to do things in this vector space. Inside this vector space, well, x is an element of this vector space, like the function f of x equals x, right? So this means the function that looks like this, right? And okay, what's its? Let's calculate some things with this. What's its norm? Well, x inner product x. We have the definition is integral of x times x dx, so minus 1 to 1. That's integral x squared dx, which is x cubed by 3, 1 minus 1. And this is a third minus a third, which is 2. Okay. Somebody asked, any subspace can be an inner product space. Yeah, any vector space can be. But the key is you have to specify the inner product and check that it specifies the property. Okay. You have to add this additional structure of the inner product. Okay, so what this means is that the length of this vector x is square root 2 over 3. Okay, now here's another vector in the space, x squared. That's a continuous function on the interval, right? What's its inner product? Oh yeah, somebody asked what CTS means. It means continuous. So let me clarify this. Yeah, C minus 1, 1 means continuous functions defined on minus 1, 1. That's a vector space. Okay, so here's x squared is another such example. What's its inner product with x? Well, let's just calculate it, right? The definition is given. It's x times x squared dx. It's 1 to 1. That's integral x cubed dx minus 1 to 1. And I could calculate this. I mean, okay, this is x to the 4 over 4 minus 1, which is 0. Okay, but now the whole point of inner product spaces is these are some calculations with the inner product. What these imply is that I can think of these vectors as having lengths and angles, just like I did with dot products, right? And everything will work the same way. So the picture associated with this is that, well, there's some vector x, and actually its length is square root 2 over 3. And then there's another vector, x squared, which is orthogonal to x. And these vectors live in the C minus 1, 1. Okay, so this is, it's kind of a crazy thing, right? Functions, we don't think of them as being geometric objects. But this is the power of inner product spaces. Once you have an inner product, once you have something that has properties 1 through 4, you can define this inner product and actually everything works. You can legitimately think of it as being, things that are perpendicular and so on. Why is x squared orthogonal to x? Well, I calculated the integral, it's 0. Right? I calculated the dot product. The dot product, the inner product is 0. Well, okay, so let's follow this, right? X, inner product X. What's the definition? The definition is written up here, right? So F is equal to X, G is equal to X. All right, so therefore X inner product X is integral of X times X dx, which is integral of X squared. If you graph the functions, is there anything to indicate they're orthogonal? Yeah, there is something actually, but in general, there's not. In this particular example, there is, but in general, there's not. I'll get to that in a moment. In general, you have to compute the integral. Okay. Why did we switch our bounds? What does that mean? Oh, sorry, my mistake. This should still be 1 and minus 1. Okay, so I mean, all that's going on here is I'm defining a new concept. I think maybe the reason people are confused is you're trying to say like, you know, why is it orthogonal? Well, it's orthogonal because orthogonal means, I mean, let me just say it here, right? So in this new context, what does it mean? You know, two vectors are orthogonal is the same as saying their inner product is 0. That's what orthogonal meant for dot product, right? So when I mean everything in this blue box comes along, I literally mean everything. So that's why I'm saying here that, you know, this implies that X is orthogonal to X. Does that make sense? Because the inner product is 0. The notion of orthogonality depends on the inner product. Geometrically, you have to make a picture in your mind. It looks like this. So this is what I'm sort of asking you to do. I'm asking you to make a new kind of picture in your mind of functions. This is the geometry, that they're sitting in some vector space and they're orthogonal. And I'm asking you to form this picture of a right 90-degree angle of these functions. Okay, good question. Are they orthogonal under this specific inner product or all inner product? Only this one, right? So this notion depends on the inner product. Can we make inner products that show us other relationship with vectors? Yes, okay, maybe that's a good question. There are many other inner products on Rn. Okay, so let me show you one more example. Inner products are not unique. There are tons of inner products on any vector space. So here's another example. The vector space would be R3. And let's define X inner product Y to be X1 times X1 Y1 plus 2x2 y2 plus 3x3 y3. That's a legit inner product. It's not the same as the dot product, but everything still works. Okay? There are actually tons of inner products on Rn, infinitely many actually. And for each one, you get a different notion of orthogonality and you get a different version of chapter 6, all of which make sense and work. Okay. Any more questions about this or this example? So you're going to do some homework problems regarding example 2 where you'll get a better idea of what this means, but please ask more questions. It's a little bit mind-blowing. But the different notion doesn't mean 90 degrees between them, does it? Yeah, so this notion is has a different notion of orthogonality. Right? For example, I don't know, let's look at two vectors. Okay, let's look at the vector. Well, okay, how do you, so let's look at the vector. What's a good example? Fine, let's look at the vector 1, 1, 0. and the vector 1 minus half 0, right? So their inner product in this case is actually 1 minus half times 2, minus half times 2, which is 0. So these are orthogonal in the new inner product. Okay, but they're not orthogonal in the standard inner product. Okay, and what I'm telling you is that, I mean, if you're living in this universe where this is your inner product, it's fair for you to think that these are orthogonal. Okay, even though they're not in Euclidean geometry. I mean, this is one of the things that happens in higher level math. Geometry is not unique. What's the significance of orthogonality in different inner products? The significance is once you have orthogonality, all of this stuff still works. You get all these theorems like the best approximation theorem, the projection theorem, Gram-Schmidt, blah, blah, blah. You get all of that stuff in whatever your inner product is, and that's useful. That's the significance. I mean, in the end, you know, these pictures are just for visualizing, right? These right angle pictures, they're just for viewing things in our mind. The real payoff is you can use this to calculate things. Okay. So now we will get to our main example. Okay, so this is like one of the greatest hits of mathematics. It's like one of the most powerful things in math. And let me set the context by relating it to something you may already know. So let's recall Taylor series, right? So what does that mean? Well, you have some function f, and you can expand it as a series at around a particular point, right? So you can write it as some f of a plus f prime of a plus a. Okay, and that doesn't always work, right? So so this converges under some conditions. So for example, the function better be differentiable, right? You better be able to keep taking derivatives, otherwise it doesn't even make sense. And okay, of course you studied when this converges and whatnot. And what does it allow you to do? Well, allows so okay, maybe you can say another thing. This is an infinite series, but if you truncate it, then you can approximate f by a polynomial, right? So approximates f by polynomials. So by truncating the series. Yeah, math 1b, math 1b. Approximates a function by polynomials, but only near this point a, right? It doesn't work for unless you get lucky, like with the exponential function, it generally only works near a fixed point. Okay, so that's Taylor series. So in mathematics, there are two main kinds of series. The first is Taylor series that you already learned about. And the second is Fourier series. So let me tell you what Fourier series is. So Fourier series. So here you're given a function on a whole interval, which for convenience will be the interval minus pi to pi. Okay. Instead of approximating by polynomials, you approximate by sines and cosines. So sine x, sine 2x, dot 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 cosine x, cosine 2x, cosine nx, sines and cosines with different frequencies on the whole interval. Okay. Now, the differences between Fourier series and Taylor series from a very high level are, so go back to Fourier series. Fourier series approximates a function by polynomials near a fixed point A, so it's local. And you need f to be, I would say, very nice for this to work. In particular, infinitely differentiable. I'll tell you what the coefficients are. Yeah, there will be coefficients. Okay? Yeah, by times coefficients. Okay. The main difference in Fourier series is, well, first of all, the functions are different, not polynomials, sine and cosine, but also it's on the whole interval. It's not just at near one point. And this is, well, also the real difference is this also works for rough functions. Okay, so functions that may not be differentiable on the whole interval, for example, or may only be differentiable once. So that's a high level, but let me now tell you what it is. Okay. So, okay, I mean, the kind of thing we're going to end up doing is you're going to be able to write some function non-differentiable, like absolute value of x. Yes, non-differentiable on the interval. This is going to be, I mean, we'll prove this in a moment, but what you actually end up getting is, what is this? Yeah, this is going to be, yeah, this is going to be, just make sure I get the normalization right. Yeah, it's going to be a half minus 4 over pi times yeah, cosine x plus 1 over 9 cosine 3x plus 1 over 25 cosine 5x, et cetera, et cetera, et cetera. Okay, this is a crazy looking identity. When Fourier first published this, people thought it had to be wrong, right? The thing on the left is not even differentiable. It has nothing to do with trigonometry. And the thing on the right is a bunch of cosine. So we'll see how to do this. Now, this turns out to be a linear algebra thing. It turns out to be an inner product space thing. So what's the setup? What's the inner product space? Let's define the inner product. So I'm going to define a vector space, V sub phi, be the set of functions from minus pi to r with two conditions, which are a little bit technical, but I mean, I will, at least you'll see what they mean. I won't explain why they come into the proof. So all functions so that f is piecewise continuous. Okay. Piecewise continuous means what you did in Math 1b, functions that, have a finite number of jumps like this. So discontinuous at finitely many points, and f prime is piecewise continuous. Okay, so that means differentiable except maybe at finitely many points. and the derivative is continuous except at maybe at finitely many points. So for example, this absolute value function x is in this vector space V, right? Because what does it look like? It looks like this. And it's not differentiable at one point, namely here. But except for the one point, it's differentiable everywhere, right? So that's a vector space. And somebody asked, what's x's coefficient again? Okay, I'm not sure I understand what that means. Oh, x coefs. Oh, I see. This means times coefficients. So with possibly multiple. So somebody, yeah. So somebody, I think asked. Somebody thought I was going to literally write the function as just sines and sum of sines and cosines. So I just mean with coefficients. I'll tell you what those are later. But the example is really what's written here, right? I wrote absolute value of x as a series where the terms are some sines and cosines with some coefficients. Okay, so that's a vector space. Any questions about the definition of the vector space? Okay. So now let's just look at some things inside this vector space, right? Well, certainly sine x is in there. Certainly sine any, integer times x is in there. So are the cosines. They're actually infinitely differentiable. They're really nice. So is the constant function, 1. That's just a function that's 1 everywhere. Those are nice functions. But then there's a bunch of other stuff in there, like the absolute value function. That's not differentiable. And then you can even have a step function. So let's call that s of x, which is going to be 1 if x is greater than or equal to 0, and minus 1 if x is less than 0. Okay, so okay, maybe I'll just specify the full interval. Oh, sorry, oops. Okay, so that function looks like exactly what I wrote over there. So those are some functions that are in this vector space. Some of them are rough, like the step function. And some of them are really smooth and nice, like the trigonometric function. Okay, so any questions about why these are in the vector space? What would happen if you took the derivative of the right-hand side? You mean of this function? The derivative doesn't exist at 0. Okay, and that's okay because piecewise continuous means, and maybe I should clarify this. Piecewise continuous means f prime exists except possibly at finitely many points. Okay. Somebody said delta Dirac function. Okay. Yeah, that's not really a function. You're right, but let's not get into that in this course. Okay. Another person asks, why are sine and cosine piecewise continuous? Piecewise continuous means except possibly at finitely many points. So if you're continuous, you are piecewise continuous. Okay, you can post questions in the group chat, by the way, rather than privately. Okay, so piecewise continuous includes continuous. Okay, at up to finitely many points. Okay, good. Somebody commented, I think f prime x equals 0 on the whole interval in this case. You mean the step function? Yeah, let's just calculate it, right? So S prime X equals 0 if X is not 0. But at 0, it's not defined. Wait, what? I see. You're talking about this. So what's your claim about this? I see. You're saying if you take the derivative at 0, then the right-hand side has derivative 0, and the left-hand side is not differentiable, right? Yeah, we'll get to that in the next lecture. I haven't said what you can do with a series like this. I haven't said you can differentiate it term by term. Okay? But it's a very good question. Keep it in mind. Somebody said if you have a function where you have all points not continuous and elsewhere continuous, no, piecewise continuous means continuous everywhere on the interval except at finitely many points. So, okay, let me make it very clear. All examples here are piecewise continuous. Am I missing the question? All examples written here are piecewise continuous. Because if you ignore a finite set of points, they're continuous and the derivative is continuous. I'm sorry, am I misunderstanding the question? If you take derivative of absolute value and evaluate at 0, it does not exist, but right-hand side has a value. These are all very good questions. I will tell you what exactly it means for this equation to even, I'll tell you in what sense this equation is true, right? You're used to saying if you have an equation, you can differentiate both sides term by term. But in this case, it's a little bit subtle because this is an infinite series. And I haven't told you that you can differentiate an infinite series term by term. Okay, we'll talk about that in the next lecture. Okay, I see. Somebody is asking if there's an interval on the function that is discontinuous and the rest of the function outside the interval is still piecewise continuous. Yeah, if you define an interval that doesn't contain, you're not allowed to be discontinuous on a whole interval, right? That's an infinite number of points. The key is you're only discontinuous at a finite number of points. Does that answer the question? Okay. So that's the vector space. Now let's look at some interesting, let's put an inner product on this space, right? We'll just use the same integral one that we looked at earlier, except from minus pi to pi. You can check that this is an inner product. I mean, we kind of already checked a couple of the properties. So now let's do some computations with some of these vectors in this vector space, right? So yeah, so the key observation is, let's look at the following function. So let's look at the functions cosine nx, where n goes from 1 to infinity, 0 to infinity. So that in cosine 0 is just a constant function equal to 1. And let's look at the sine functions. Again, n goes from 1 to infinity. That's an infinite set of vectors in this vector space. Okay. Key observation is these are an orthogonal set. With respect to, you know, the inner product defined. Okay. Well, you know, what does that mean? Well, it means that if you take any two distinct vectors, their inner product is 0. Somebody asked, how did you get the values of n? I defined it that way, right? I mean, so literally, this means the vector is, you know, 1 cosine x, cosine 2x, dot dot dot, and then sine x, sine 2x. No, n must not be the same for both sine and cosine. So, okay, maybe you're not familiar with this notation. This notation literally means cosine nx, I'm making a set out of cosine nx for all integers n. This is an infinite set. So yeah, going back here also, I mean, this is true for any integer n, right? So I actually have infinitely many vectors in this set. So, I mean, yeah, if I wanted to be clear, I could make, you know, the second one m, but m and n don't have to be the same. Okay, so let's check this. Well, so for the proof, actually, I'm going to need one. There's a notion that will make the proof a lot easier, and that's the notion of even and odd functions. So even just means f of x equals f of minus x for every x. And it's odd if f of x equals, sorry, you know, I should write it this way, f of minus x equals f of x, and odd if f of minus x equals minus f. Okay. So what's an example of an even function? Well, x squared, right? And this even function just means if you reflect it around the y-axis, it doesn't change. Another example is cosine x, right? So cosine x looks like this. An odd function has the opposite property. So x cubed is an odd function. If you reflect it across the y-axis, it flips sign. And sine x is an example of an odd function, right? So sine x looks like, okay, it's a horrible picture, but you know what I mean, right? If you flip, sine of minus x is minus sine of x. Yeah, somebody already anticipated what I'm going to say, but I'm going to say it in a moment. But for now, just focus on what even and odd functions are. They're a very simple concept. And one nice thing is that the set of even functions is a subspace. And v by odd are subspaces of v pi. Okay, somebody asked the question, do odd and even functions only exist in v pi? Well, I'm defining them in v pi, but really this can be defined in other, can be defined for any function on R or on an interval. But I'm defining it for v pi, so it can also be defined. So this is a general concept that will come up later in life for many people. Somebody's saying sine is odd and cosine is even. Yes, cosine is even because cosine of minus x is equal to cosine of x, and sine is odd because sine of minus x is equal to minus sine of x. Correct. Okay. So now, here are some general properties of even and odd functions. One is you take the integral of an odd function. So let's say on this interval, what's it going to be?
0.
0, because it's exactly negative on one side of what it is on the other side. You can see this in the picture, right? If you have, let's say, the x cubed function, well, the integral is like this area plus this area, but they have opposite signs. Another easy property is if you take an odd function and multiply it by an even function, get an odd function. You can just check that from the algebraic definition. Just plug in minus x, you get 1 minus sign out. And similarly, odd times odd equals even, because you get 2 minus signs. These are all quite easy properties. Okay, so now let's go back to our key observation with this slight simplifier, odd and even functions. Actually, it comes up a lot. Let's go now to proving this key observation, that these sines and cosines form an orthogonal set. So let's do it on a new slide, actually, since it's important. Well, I'm going to first, so let m and n be non-negative integers, or actually let m and n be non-negative integers. Well, there are a few cases, right? So what happens if I take an inner product of cosine nx with cosine, with sine mx? Well, what's the inner product? It's an integral, right? This is where the even and odd stuff comes in, as many people are saying in the chat. This is even, this is odd. So the product is odd. But the integral of an odd function on this interval is 0. So all the cosines are orthogonal to all the sines. So this implies that cosine nx is orthogonal to sine mx. What about two cosines but with different m and n? Okay. Somebody asked, wouldn't they be odd and even if m and n were negative? Yeah, they would be. But we're just taking them to be integers. If you want, you can take them to be negative. That's not really okay. So now somebody's asking, is the first thing only the case when m equals n? No, it's always true for any m and n. Right? Cosine nx is always even. Sine mx is always odd. Doesn't matter what m and n are. Okay. So now let's do the second. Let's look at two cosines. What is this? This is cosine nx cosine mx dx. And now we need to do some math 1b. So anybody know how to do this integral? Product to sum formula, exactly. So use the trig identity, which is a product to sum formula, to get that this is minus pi to pi cosine of n plus mx plus cosine of n minus mx dx. Okay. And now you split into cases, right? So there are actually three cases. So if m is not equal to n, then these are both cosine some integer times x, right? Okay. And well, I mean, you can with cosine pi is minus 1. So the cosine looks like this. And I mean, you can check. So the integral of cosine x on this interval is actually 0. And actually, cosine of any integer times x, the integral is also 0. So this is 0 if m not equal. Because, you know, integral cosine any kx is equal dx minus pi is 0. You can check that if the picture is meant to you. But I presume you did that in math only. But if m is equal to n, then what happens? Any thoughts? Okay, you get pi. That's right. Now the reason is, well, if cosine is equal to n, you get half integral. So the first term goes away because n plus m is some non. I'm sorry. If m is equal to n and okay, both are correct. If m is equal to n and not 0, you get pi. Let me just write the answer. because it becomes the integral of cosine 0x plus integral of cosine kx for k not equal to 0, half. This thing, the second term goes to 0 by the same reasoning as in the first case. And the second term is just 2 pi divided by 2, which becomes pi. Then there's one more case, which is if m is equal to n is equal to 0, you get half integral cosine 0x plus cosine 0x dx, and that's 2 pi. Okay, these are some trig integrals from Math 1B or whatever. Okay, so that's what happens with the cosines. And the same sum to product reasoning you do with the sines. This equals 0 if m is not equal to n, and pi is equal to n. You don't have this special case of 2 pi for sine, because the constant function 1 is not a sine of anything, right? Cosine 0 is always equal to 1, but sine of 0 is just 0, and that's not included in that set. So what's the upshot of this? Well, it gives us a pretty interesting picture of these vectors living in this vector space V pi. There are infinitely many of them. Any two distinct ones are orthogonal because their inner product is 0. And actually, by plugging in the m equals n cases, we actually even computed the norms of the vectors. Right? So this implies that norm of cosine nx squared is equal to pi if n is not equal to 0. And okay, norm of the one function is equal to 2 pi. Right? Because that's the inner product of the function with itself. And this implies that the norms of the sine functions are also all the same. They're just equal to pi. Okay. So let me draw a picture to make this clearer now. You have the following picture of V pi. So first of all, there are two big subspaces that are orthogonal. These are the even and odd functions. Okay. The cosines live in the even functions, the sines live in the odd functions. And they're all orthogonal to each other and to the other subspace, right? And here you have some, you have the one function, then you have cosine x, then you have a cosine 2x, infinitely many. And here you have some other functions. You don't have the one function, but you have sine x, sine 2x, and 3x, whatnot. And V pi looks like this. And so there are these orthogonal sets living inside these subspaces. And they're all not 0, right? So all are non-zero, and their pairwise orthogonal. And that means that they're linearly independent. because orthogonality implies linear independence. Somebody asked a good question, is there some value that lives in both spaces? Yes, 0. This goes back to chapter 6. So it seems a little abstract, but it's all just chapter 6. If you have two orthogonal subspaces, for a vector to be in both of them, it has to be orthogonal to itself. That means this norm squared is 0, so it's a 0 function. I mean, okay, that uses this fact that if a norm of a function is 0, it's 0. Okay, so that's a picture of what we just proved. Good question. Do these subspaces have functions other than sine and cosine? Yeah, I mean, here's another function that's in the even subspace, absolute value. And here's another function, the odd subspace, s of x, the step function. Right? Yeah. I mean, okay, s of x, technically at 0, it's not odd, it has to be 0 at 0. So did I make it 0 at 0? Let me do it this way. Minor difference. Okay. Okay, somebody's saying they don't get what a Fourier series is. That's because I haven't told you what it is. So you're not, there's nothing wrong. I'll now tell you what it is. Okay. So the conclusion is sines and cosines form an orthogonal set in V pi. That's easy to check. The thing that's a miracle is that they actually form an orthogonal basis. So I'm going to put this in quotes because it's a little different from the notion we saw earlier. If you allow infinite linear combinations. Okay. So that's, let me now tell you finally what a Fourier series is. So a Fourier series is a way of making this fact rigorous, that the sines and cosines are actually an infinite orthogonal basis. Okay, so what's the motivation? So recall if you have some vectors are orthogonal basis of Rn, then every x in Rn has, well, can be written as a unique linear combination so let's just put norm squared here. Okay, so Fourier series is a generalization of this fact to this new setting of V pi. Okay, so here's the definition. If function f is in V pi, its Fourier series is defined as the following series. Let's call it fs of f. So it's a series that has some coefficients Okay, so formally that means it's a naught over 2 plus summation n goes from 1 to infinity, a n cosine nx plus b n sine nx, where these coefficients have a very specific form, where the first coefficient is the inner product with the 1 function of f divided by the squared norm of the 1 function. Okay, so we calculated that, right? So that's I mean, we calculated that somewhere on the previous page. So yeah, the norm of the 1 function is 2 pi, right? So you have so this is 1 over 2 pi integral minus pi to pi f of x dx. An is defined to be the normalized inner product with the cosine function. So let's put norm squared. And we calculated that, right? What's the norm squared of the cosine function? It's pi. And now Bn is what it is for the sine function. And again, that also had norm squared equal to pi. Okay. So what we're doing, I mean, the way to think about this is just an infinite dimensional generalization of this, right? If these things were an orthonormal basis, what would be the formula for the coefficients? It would be this, right? If they were, I haven't defined what it means for an infinite orthogonal basis, nor am I really going to. I'm just going to define this Fourier series. Okay, so if this behaved like an orthogonal basis, this would be equal to the function. Okay, so maybe before I say anything about that, let me just calculate for an example, right? So the function I'm going to look at is the step function. So s of x, which is this function at 1 if I'm sorry, it was minus 1 and 1, right? Yeah, okay. So technically to make this odd, I would have to define it to be 0 at 0. So let's just, it's not really important. Okay, so so let's look at this function, which is 1 if x is 0 to 5, minus 1 if 0, and 0. Right? That's not continuous at 0. So it's a function that looks like that, something at 0. So what is its Fourier series? Well, let's look at the coefficient. So by the way, you might be the reason for this funny 2 here is just so you don't have, because there's a 2 in this integral, and you just want to be able to normalize all your integrals by 1 over pi. That's the only reason there's a 2. It's not a deep thing. It's just that the constant function has twice the squared norm, the sine and cosine. That's a fact. Can't get around it. So let's calculate the Fourier series. Okay. So what are the coefficients? So a naught is going to be the integral over 2, or just naught actually, is going to be 1 over pi, the integral of s of x dx, right? But I actually immediately know this is 0, right? Because it's an odd function. Okay. What about the ANs? Well, the ANs for n not equal to 0. The ANs are 1 over pi. So okay, just to make it well defined, I should say m and n are just going to be non-negative integers, right? So these are all, I'm not considering negative n's here. Okay, so n, this means n greater than or equal to 1. An is 1 over pi integral minus pi of pi cosine nx s of x dx. Anyone know what that is?
Zero.
0. Why is it 0?
Odd times even is odd.
Yeah, this is odd. This is even. So this is 0 also. Well, but something better, interesting better happened here. 1 over pi now we have sine nx s of x dx. And now they're both odd. So this integral, I don't know if it's going to be 0, right? So how do I compute it? Well, I have to break it into cases, right? So this is integral from minus pi 1 over pi, integral from minus pi to 0. And on minus pi to 0, s of x is minus 1. And then you have an integral from 0 to pi, where it's 1. Right? But that's actually just the same integral twice, because if I flip the limits on the first integral, I pick up another minus sign. So this is just 2 over pi integral sine nx dx minus pi. And what's that? Well, I guess you learned how to do that I learned how to do that a long time ago. But now it's 2 over pi. So the integral of sine nx is minus cosine nx over n. Oh, I'm sorry, this should be 0. And so if you figure out what that is, well, what is that? So that's 2 over pi minus cosine n pi plus cosine 0 over n. And now cosine n pi, actually, the value depends on whether n is even or odd. Right? So this is, you figure this out, this is going to be 0 if n is even, and 4 over n pi if n is odd. So the conclusion of this whole calculation is that the Fourier series of this function s is equal to a bunch of zeros, and then only the signs have coefficients. So it's, and only the odd ones. So you have 4 over pi sine x plus 4 over 3 pi sine 3x plus 4 over 5 pi sine 5x, etc. That's the Fourier series. Now, what is this good for? It's just some old series that I defined, right? So I'll just state the punchline, and then we'll look at more examples and do some cool things next time. The punchline is that is essentially equal to the. This is
Wait,
the
do on the bed.
Really?
And the theorem is
One.
if f is any function,
Start at 6.
then the Fourier, then two things happen. The Fourier series always converges.
Don't ever put water here, ever again.
And when it converges to the right thing. So it equals f of x if f is continuous at x. If it's discontinuous, it equals the next best thing, the average of the left and right limits. And you have to also handle the endpoints. So here it's the limit of the lower endpoint from above plus the upper endpoint from below at endpoints. Okay, so this is a deep theorem. We're not going to prove this theorem. But the meaning is that up to these little caveats at discontinuous points, which I'll call star, is that every function is actually equal to its Fourier series up to these caveats. And remember, the coefficients are these very specific things, right? So A naught is and okay, A0 is equal to half of that, right? Right? So the meaning is that for all purposes, this is like an orthonormal basis. So it's an amazing thing. It's an infinite orthonormal basis for a very large space of functions. And this is like one of the most important things in physics. It says you can approximate a huge class of functions with sines and cosines, which are like the nicest functions. And in that sense, it's a lot deeper and more powerful than Taylor series. I mean, they have different uses. But we'll do more examples and applications next time. So that's all for today. Any more questions?
Professor?
Yep.
Are we getting to PDEs?
We're just going to very briefly mention them next time. But we're not really going to do them in this course. Somebody asked, why is A naught over 2? That's just a convention here. Because the norm squared of the 1 function is 2 pi, whereas the norm squared of cosine nx is 1 pi. So we put the 2 here so we have a unified formula. I mean, I didn't write the unified formula here, but there are 2 different ways of writing these AIs. Another way is just writing an equal to 1 over pi integral cosine nx f of x dx. And bn is equal to 1 over pi. And so if you want this formula to, these 2 are the same, but if you want this formula to hold, this is true for every n, including n equals 0, the left side. Then you need that 2, that's it. Could I go over the meaning once again? The meaning is sines and cosines are an orthogonal basis, in quotes, of this space V pi. And the reason it's in quotes is there's this star here. The functions are not literally equal, right? They're almost equal. I mean, if the function is continuous, they're equal actually. But if it has discontinuities, it's, there's a slight adjustment at the points of discontinuity. And the other thing is it's an infinite series, right? Technically, basis means linear combination. Linear combination means a finite sum. So this is an infinite sum. That's why it's in quotes. But the meaning is really, this is how I think of the meaning. Sines and cosines are an orthonormal basis of essentially all reasonable functions. What if you're interested in values outside the interval? We'll get to that next time. Any other questions? Could I go back one slide? Yes. I got my Wi-Fi back, and actually I even got upgraded Wi-Fi, so yeah, work done. Why do you need them to be integers? Well, certainly this stuff that this calculation that I did here, not here, this calculation here, this only works for integers. If m and n are not integers, this stuff is not true anymore. Okay. It's a good question. You could imagine what happens for m and n not integers, but these really use that they're integers. The orthogonality relations use that they're integers. Anything else? Okay, great. Well, oh, somebody else. What was the point of the other two cases if we just wanted to show they're orthogonal? Oh, well, the point of the other two cases is to calculate the squared norm, right? So this m equals n case, this is what tells you the squared norm. And you need the squared norm, right? You need to, I mean, in this formula, you need to divide by the squared norm, if essentially to make them unit vectors. Why are m and n not negative? Well, we define them that way. You could take them to be negative, but then you'd have to worry about, cosine minus nx is, I mean, there's no need, right? Because cosine minus nx is the same as cosine nx, so just be redundant. And sine minus nx is just minus sine nx, also redundant. So there's just no need to consider negative values. And actually, this is important. If you took negative values, they would no longer be linearly independent. Somebody asked, what if you choose some other odd and even functions other than cosine and sine? Great question, but cosine and sine are kind of magical, actually. There aren't too many choices of functions for which this works out. I mean, okay, actually that's not true. There are lots of other choices, but cosine and sine are the nicest ones with the best properties. I mean, in some sense, they're the nicest functions, right? You can differentiate them as much as you want. You can integrate them. The formulas are nice. They have many nice properties, and they have also physical meaning. Okay, so I guess that's it for today. So see you next time.
So can I ask a question?
Yep.
Yeah, so like I want to ask like, is there any kind of like a specific like demand that we need to define the inner products as the integral between negative pi and pi? Like if I define the operation of inner product in other way, does the Fourier series work?
So Fourier series really is specific to inner products that are defined as integrals.
Okay.
You can do it over other intervals. It could be -1 to 1. We'll do that next time. But Fourier series really is something special about this type of inner product with integrals. So yeah.
Okay.
I mean, generally people refer to this process of defining an inner product and having an infinite orthonormal basis. They refer to it as generalized Fourier series. And there are tons of other things you can do, but Fourier series refers to this one.
Mm-hmm. Thank you, Professor.
Yep, thank you. Okay. So somebody asked about grading. I'll discuss that in an email.